For something like 6x, we know that the derivative is just 6 because the slope of that line is 6. You could also see it by using the rule because 6x is really 6x to the first. And the derivative would be 6 times 1 times x to the 1 minus 1. But that's just 1 times x to the, or 6 times x to the 0, which is just 6. So you can always use the power rule, you just don't always have to. Right? Like, we don't really need to use the power rule for the derivative of 6x. We know that line has a slope of 6. But for other things, we do. And so what I really kind of want to emphasize here is that we've got some other rules for derivatives that we kind of just use without ever talking about using them. It's not like it's a secret or anything. It's just we don't. So let's say we had something like 5x to the 10th. Can I see your symptom survey, sir? Thanks. Plus 6 times the square root of x minus 5x cubed. Thank you. Thank you. So there's a rule. We know that the derivative of x to the 10th is just 10x to the 9th. And what are we going to do with that 5? Well, when we take the derivative, the 5 just kind of hangs out. 5 times x to the 10th derivative is going to be 5 times 10x to the 9th. Now, normally nobody ever does it like this. We usually just say, oh, the 10 multiplies the 5, and you get 50 x to the 9th. In a similar way, this is 6 times x to the 1/2. And the derivative is going to be 6 times 1/2 times x to the negative 1/2. And then over here, you're going to have a minus 5 times the derivative of x cubed is 3x squared. So for each of those, I'm just using the power rule, and then I'm going to multiply by this constant multiple. So this is going to simplify to 3x to the negative 1/2 minus 15x squared. And what I want to point out here is that I've actually used two rules without, I guess I kind of talked about one of them. One of the rules I totally used was that if you have a constant times a function and you take the derivative of it, the constant just sticks around. Thank you. Thank you. So the derivative of 5 times x to the 10th is 5 times the derivative of x to the 10th. The other rule that I totally didn't even talk about that I definitely used here is that when you have a function that's a whole bunch of things added together and we're differentiating it, you're just going to differentiate all the pieces and add or subtract them together as is appropriate. And that's something we do all the time, right? We just go, oh yeah, you got this plus this plus this. You're going to take the derivative and you're going to get the derivative of this plus the derivative of this plus the derivative of this all the time. So let's look at some more. And I guess, I mean, we could totally write the rules. Here are what the rules look like if you write them out. If you take the derivative of f of x plus g of x, it's equal to the derivative of f of x plus the derivative of g of x. And it's true whether it's addition or subtraction. And then the other rule that we kind of used without really saying anything about it is if you have the derivative of a constant times a function, it's equal to the constant times the derivative of the function. Rules we use all the time and never really talk about. And then I suppose the last one I should mention here, which isn't really here, but I'm going to say anyway, is that if you're taking the derivative of just a constant, so if your function is a constant, what's the derivative going to be? Yeah. So equal to 5, equal to 7, equal to 0, the derivative is going to be 0. Before I forget to mention, please fill out the attendance when you have a chance. Same for you all on the Zoom. Fill out the attendance link when you have a chance. All right, let's do a few more examples, and then we will talk about some other derivative rules. And let me switch things up to being sideways, because that's the way I like to be oriented here. It feels weird to be oriented the other way. All right. Let's say we had something like this. F of x equal to 4x to the 7th plus 2 over x to the 3rd plus 5 over the cube root of x plus e to the, e to the third. All right. It's usually a good idea to simplify things before we differentiate them. Specifically, I want to point out, and I don't remember if I said this last time or not, but I'm going to say it again. If you're taking the derivative of something like 2 over x to the third, so if your function is just 2 over x to the third, the derivative is not 2 over 3x squared. We can't just differentiate that x to the cube in the denominator. We have to write it as x to a power not in the denominator. So I'm going to rewrite all of this as 4x to the 7th plus 2x to the negative third. And then 5 over the cube root of x is 5 over x to the 1/3, which is 5 times x to the negative 1/3 plus e cubed. And now everything that has an x in it is written as x to a power. We can use the power rule on all of those things. So my derivative, 7 times 4 is 28 times x to the 6th. Negative 3 times 2 is going to be a minus 6x to the negative. Yeah, thank you. Negative 4, right? The negative powers get more negative if we subtract 1 from them. And then this one's going to be a little bit of work. Let's see. 5 times negative 1/3 is minus 5/3. And then we're going to subtract 1. And what's our new power going to be? Thanks. And then what's the derivative of e cubed? Big old 0. So don't get fooled. I imagine many of you probably know that the derivative of e to the x is e to the x. It's totally true. But there's no x's there. So if you see a thing, even though it might look like a function, that's a constant. I don't know what it is exactly, but it's probably like 25. Maybe a little less. I don't really know. But it's something that never changes, right? E cubed is always the same number every single time you look at it. It doesn't change. And its derivative is 0. Yeah. Sure. Yeah. So like how I got from here to here, or how I took its derivative. Sure. So what I'm really doing for the derivative of that, the derivative of that is going to be 5 times the derivative of x to the negative 1/3. And the derivative of x to a power is going to be that power times x to the 1 less power. So I'm going to do negative 1/3 minus 1 as the power. 5 times negative 1/3 is negative 5/3. And then for the power part here, negative 1/3 minus 1, I need the common denominator. And a lot of times we're not going to show that work because we do it so frequently. But what we're going to see is it's going to be negative 1/3 minus 3/3. And negative 1 minus 3 is negative 4. So negative 1/3 minus 3/3 is negative 4/3. These pens are not pleased with my purchase. I mean, I didn't buy them, but like, I'm not pleased with my choice. I chose pens that are not excellent. So does that clarify? Cool. Let's look at some more examples. Again, if you have questions, don't hesitate, right? I'm happy to clarify anything. So let's look at this function. G of x is x squared plus 3x times x to the 4th plus 2. And I'd like to take the derivative. And I want to point out, well, in fact, I'm going to point out over here. Here's what the derivative isn't. The derivative is not 2x plus 3 times 4x cubed plus 0. Or more generally, if you're taking the derivative of a product, you can't just take the derivative of each piece and multiply it together. Totally works if you're adding things, right? Like a function plus another function, the derivative is just the derivative of the first thing plus the derivative of the second thing. But for things multiplied together, it's not the case. Let's see. I'm not going to find g prime of x just yet. I'm going to simplify before I start finding g prime. So I'm going to multiply this out. X squared times x to the 4th is x to the 6th. X squared times 2 is 2x squared. 3x times x to the 4th is 3x to the 5th. And 3x times 2 is 6x. And I probably should have written this in the more standard order, but I didn't. So now my derivative is going to be derivative of x to the 6th is 6x to the 5th. Derivative of 2x squared is 4x. Derivative of 3x to the 5th is 15x squared. And the derivative of 6x is 6. If I was writing this in the standard way, I'd write it as 6x to the 5th plus 15x. Oh, I made a mistake there. What should my power actually be? Yeah, I might have said 4. I don't remember actually, but I certainly didn't write 4. And I just want to really kind of make it more obvious. That's not the same as that, right? If you multiply this out, 2x times 4x cubed is 8x to the 4th, and 3 times 4x cubed is 12x cubed. Definitely not the same. Okay. But that kind of begs the question. Well, we'll get there in a minute. Let's keep things in order. Have you guys started talking about the product rule yet? Okay, cool. We're going to get there. I'll show you a couple more examples. Because although it's perfectly fine to use the product rule in an example like this, you might not want to. It might just be easier to multiply it out first. So, and this is kind of true about a lot of things. It's great to use the tools we have, but sometimes you don't need to. Like, for example, there are lots of limits where you could use L'Hopital's rule, which we hopefully will learn about in this class, but that doesn't mean it's always the best choice. In fact, just as a quick aside here, I will tell you all, but thank you. A limit like this, say sine cubed of 2x over 4x cubed, you could definitely use L'Hopital's rule 3 times, and it would be incredibly awful. There's a much simpler way of doing a limit like this. I think we've talked about ones like this, right? The sine x over x ones where the limit's 1, right? We have, sorry, I really like, I know I talked about it in the other class, if I'm not too sure. So if I was doing this limit, I wouldn't use L'Hopital's rule. I would instead write it as sine of 2x times sine of 2x times sine of 2x times something over 4x cubed. And then what do we wish we had beneath every sine of 2x? A 2x. And then that limit ends up being 1 times 1 times 1 times 2 times 2 times 2 over 4, which ends up being 8 over 4, which is 2. Excellent question. Why do we want the 2x on the bottom? Well, I believe we have seen before, and you guys should correct me if I'm making an incorrect assumption here, but I think we've talked about how the limit as x goes to 0 of sine of x over x is equal to 1. Or more generally, how the limit as some stuff goes to 0 of sine of whatever that stuff is divided by the exact same stuff is equal to 1. I'm not doing it to get rid of the fraction. I'm doing it to make it so the stuff I'm taking the sine of and the stuff that's in the denominator, those are actually literally the same. And so when I write it this way, I have sine of 2x over 2x. So the thing I'm taking the sine of and the thing we're dividing by are literally the same exact expression. Same deal here, same deal here. And as long as the thing we're taking the sine of and the thing we're dividing by are the same, and they're both going where? To 0. That limit's always 1. Let me show you, because I think this is something that's like, please do tell me, like we have talked about this, right? Okay, but let me show you, because I do think it's worth actually, I know we've looked at this graph before, but I want to show you again because I think it's worth seeing. So check this out. Here's sine of x divided by x. And if you zoom in on x getting closer to 0, the y values are obviously getting closer to 1. But it actually doesn't matter if it's x or 3x, as long as the 3x there and the 3x there are the same. So the limit as x goes to 0 of sine of 3x over 3x is also 1, right? The y values get closer and closer to 1, but at 0, they're undefined. If I can actually get there. You guys kind of saw it, right? Yeah, there. So as long as you have sine of something over the exact same something, then the limit of that's going to be 1, as long as the something is going to 0. We could even look at the problem I wrote. Maybe that feels, oh, I'm a little worried here. They don't like sine cubed. Fine, be that way. Let's put the cube on the outside. Yeah, thank you. The denominator was a 4x cubed, not an 8x cubed. Oh yeah, that limits 2. Because really it's sine of 2x over 2x times sine of 2x over 2x times sine of 2x over 2x, which are all going to 1. And then we're left with an 8x cubed over 4x cubed, which reduces to 2. So that's what's going on there. That's how we deal with limits like that typically. And yeah, the point I was making wasn't that we should do this limit, but the point I was making is that sometimes you don't always want to use the fanciest tool you have, right? We don't, there's people like, there's like a saying, like, don't use an atomic bomb to kill an ant when you can use your thumb. It's not exactly that, but it's essentially that, right? You don't need to use a more powerful tool than is necessary. Here, you don't want to use L'Hopital's rule. It is awful. Like the second and third step become really atrocious. This is a much easier way of doing this. In a similar way, you probably don't actually want to use the product rule to differentiate something like this. It's not that terrible, but that's kind of the point. Or for example, if I had the function, say x to the 9th plus x cubed plus x squared divided by x to the 4th, sure, I could use the quotient rule if I knew what it was, but it's way easier to simplify this. So I'm going to write this as, sorry, I'm not going to find the derivative just yet. I'm going to simplify. I have x to the 9th divided by x to the 4th plus x cubed over x to the 4th plus x squared over x to the 4th. And I can rewrite that as x to the 5th plus x to the -1 plus x to the -2. And now it's not terrible to differentiate at all. It's going to be 5x to the 4th minus x to the -2nd. And then what's the last part going to be? Minus 2 times x to the what's my new power? Yeah. That's way better than doing the quotient rule. I'm kind of going to avoid the quotient rule whenever I can person. So not that we'll never use the quotient rule because it's an important rule, but it's nice to have other options. And again, I should just stress here, I want to remind you all, the derivative of this is not 9x to the 8th plus 3x squared plus 2x over 4x cubed. It's definitely not the derivative, meaning you can't take the derivative of a quotient by just doing the derivative of the top divided by the derivative of the bottom. Okay. Questions, concerns, comments? Look at another, oh yes. Let's say I have this function. H of n is r times n times 1 minus n over k, which is a function you might have seen already. You might not have. You probably will eventually if you haven't already. And I want to find the derivative. Now, let me ask you all a question. What's my variable? It's n, meaning r and k are acting like constants. So the things that the function is not a function of, those other letters, they are always assumed to be constants. So I'm going to multiply this out. Rn times 1 is Rn. And Rn times -n over k is going to be minus r times n squared over k. And I really think it's in our interest to think of this not as a quotient, but as r over k, the constant, times n squared. And then it's really, really not terrible to differentiate. The derivative of r times n is going to be r times 1. The derivative of r over k times n squared is going to be r over k times 2n. I'd probably leave it like that if I didn't need to do anything else. I mean, you could probably rewrite it as r minus 2rn over k, but that seems not super necessary. Okay, so one more example, and then we'll start talking about the product rule. Yeah. Let's find not just the derivative, but the equation of the line tangent to, what have I got here? F of x equal to the square root of x times x plus 6 at x equal to 4. So to find an equation of a line, I need two things. I need a point and I need a slope. And so far I've got like half of a point, right? Because I only have the x coordinate of my point. So let's find the rest of the point. My point is going to be x comma f of x, which is going to be 4 comma f of 4. And f of 4 is going to be square root of 4 times 4 plus 6, which is 20. So my point is 420. No pun intended there. Sorry. Those are just the numbers. Sometimes they come up. Also, totally aside, anyone here speak French or take French in high school? Okay, one person. It's totally weird how the French say the number 80. They say 80, which means 4 times 20. Totally bizarre, right? Like nobody, right? Who else does it that way? Like nobody. But it's just kind of, sorry, the 420 there made me think of the 420s and 80. So anyway, not at all important, but sometimes you get not important things from me because, hey, I can say whatever I want. Not whatever I want, but you know, not that I would say like terrible things, just to be very clear, right? Like, okay, so yeah, let's get back to the math. We've got the point, 4 comma 20, and now we need the slope. And to find the slope, we're going to take the derivative. So we're going to do, oh, but before I take the derivative, I should probably simplify this. Let's write this as x to the 1/2 times x plus 6. And then if we distribute, we're going to get x to the 1/2 plus 1 is 3/2. And x to the 1/2 times 6 is going to, I said 1/2 plus 1 because adding the powers is really x to the 1/2 times x to the 1. We add the powers. And then 6 times x to the 1/2. And then we can easily find the derivative as 3/2 x to the 3/2 minus 1 is 1/2 plus 6 times 1/2 x to the -1/2. All right, so I'm going to simplify that just a tiny bit. I like the 1/2 power for taking derivatives. Like I would definitely write x to the 1/2 for derivative purposes. But if I'm going to plug in a number, I really prefer to write the square root. You can do whatever you want, but I would really like to write this as 3/2 times the square root of x plus 3 divided by the square root of x. Because x to the -1/2 is 1 over x to the 1/2, which is 1 over the square root of x. I think it just makes it easier to evaluate things when you rewrite it that way. But whatever is better for you, right? Write it how you want. So then if I'm going to plug in 4 to find the slope at that point, I'm going to get 3/2 times the square root of 4 plus 3 divided by the square root of 4, which is going to be 3/2 times 2 plus 3/2. So here's something worth noticing. I could totally simplify 3/2 times 2 as 3. But it's actually not in my benefit to do so because I'm going to be adding it to 3/2. I already have a common denominator. I should be smart about this and be like, okay, well, 3/2 times 2 is 3/2 times 2 over 1. And that's just going to be 6/2. Then I have 6/2 plus 3/2. I already have a common denominator. That's going to be 9/2. Normally I would have been like, oh, 3 halves times 2 is just 3, but then I would have had to change it back to 6 halves to get a common denominator. So don't make more work for myself than I need to. Finally, we write the equation of the line. I'm going to do it as the point slope form. Y minus y1 equals m times x minus x1. So I'm going to have y minus 20, the y coordinate, equal to my slope times x minus 4. Usually they want you to solve for y. I would totally prefer just to leave it like this, but if we have to solve for y, we have y equal to 9 halves times x, and the 9 halves times negative 4 is going to be negative 36 over 2, which is negative 18. And then we're going to add the 20. So we end up with y equal to 9 halves x plus 2. Math feels extra hot today. All right. So, power rule. You really want to make sure it's just embedded in your brain because you're going to use it all the time. And you want to be very, very comfortable. Like, oh yeah, the derivative of x to the 9th is 9x to the 8th, right? Just it should roll. It should be like a second language or your first language. I don't know. It should be there. All right. Product rule. Before we do the product rule, let's talk about some other functions. Specifically, I think last time we talked about how if you graph sine of x, it sure looks like the derivative is cosine of x. Just as, and let me remind you, here's the graph of sine. Oh, sure, sorry. It's got a period of 2 pi. And then if we graph its derivative, right, you can see that right here, the slope is 1. At pi over 2, the slope is 0. At pi, the slope is negative 1. At 3 pi over 2, the slope is 0 again. And at 2 pi, the slope is back to being 1. And so the derivative definitely looks like and is cosine of x. And then in the same sort of way, we can kind of verify to ourselves that if we take the derivative of that, using the same sort of graphical method, well, now the derivative there is 0, because the slope of the tangent line is 0. The derivative there is negative 1 at pi over 2. Sorry, negative 1. And then at pi, the slope of the tangent line is 0. And then at 3 pi over 2, the slope of the tangent line is positive 1. And finally, back to 2 pi, the slope of the tangent line is 0. And so it looks like this. Which looks like what function? Right, let's say I took the sine function and flipped it over, which is exactly negative sine of x. So the derivative of sine is definitely cosine. And I'm going to use a different letter. If your function is cosine, the derivative is negative sine of x. Those definitely come up all the time. So the reason I'm mentioning those is because we're going to use them to ask some questions about the product rule. Like I would really like to know, and we're going to circle back around to this, if my function is, say, x to the 4th times sine of x, what's the derivative? Well, we don't have the tool for that just yet. So let's get it. So product rule. There's a lot of ways to say it. Here's one way. If you have a function f times g, And you want to take the derivative of that. It's going to be, I like to say it as the derivative of the first thing times the second thing plus the first thing times the derivative of the second thing. F prime g plus fg prime. I always think of it as the derivative of one piece times the rest of the stuff, and then you kind of do that for each piece. So it's the derivative of one thing times g, and the derivative of the other thing times f. And the reason I'm kind of saying it that way is because you can have a product rule for more than two things multiplied together. So you can also have a product rule for like 3 things multiplied together. We'll come back to this, but, well, no, I'll say it is going to be f prime times g times h plus f times g prime times h plus f times g times h prime. And generally, whenever you have a product of many pieces and you're taking the derivative, you always get one derivative and the other not derivatives multiplied together. So I'm taking the derivative of 3 things multiplied together. There's 1, 2, 3 pieces, and each piece has one derivative and the other functions left alone. One derivative, the other functions left alone. One derivative, the other functions left alone. And each derivative has to show up. So don't worry too much about this, but it's going to come back. So that's why we're kind of saying it now. Let's look at some examples. Back to our example from before. I forget what it was. X to the 4th times sine of x. So the way we're going to differentiate this is by using the product rule. I'm going to think of these 2 pieces separately. And then the derivative of x to the 4th is 4x cubed. And what do we multiply it by? Sine of x. Plus, then when we flip it, we leave the x to the 4th alone, and we multiply by the derivative of sine, which is cosine. Here's an example I like to keep in mind. If we have f of x equal to x squared times x cubed, which is really what? It's x to the 5th. We know the derivative should end up being 5x to the 4th. Well, let's actually use the product rule on this expression here to see that it really works. So I'm going to think of these 2 parts separately. The derivative of x squared is 2x times x cubed, plus, now I leave the x squared alone and multiply by the derivative of x cubed, which is 3x squared. Is that going to come out right? I think it is. 2x times x cubed is 2x to the 4th. And x squared times 3x squared is 3x to the 4th. So we end up getting 5x to the 4th. So it works. It's good to see it for a function that we already know the derivative of. We could prove the product rule. I don't feel like that's super necessary, but who would like to see a proof of the product rule? You can all say no, that is perfectly fine. It's all perfectly good because it's really fast. So how do we actually prove the product rule? I want to take the derivative, and I would just say, so I haven't been using this notation much, but it is a very common notation for the derivative. I want to find the derivative of the product, which you could also write as the product prime. Either way. Okay. So when we want to find the derivative of something and we don't know how to do it, we typically go back to the limit definition of the derivative. So I'm going to say, well, the derivative of this is going to be the limit as h goes to 0 of the thing of x plus h minus the thing of x. So here it is. So it's kind of weird to think of this, but if my function is f of x times g of x, then when I plug in x plus h, I get f of x plus h times g of x plus h minus f of x times g of x all over h. there's my limit definition of the derivative. Sometimes what some people do is they take an extra step and say, I'm going to call this capital H of X. And then the derivative of capital H of X is the limit as little h goes to 0 of H of X plus H minus H of X all over H. And then they're like, oh, but H of X plus H is really f of X plus H times g of X plus H. And H of X is really f of X times g of X. So sometimes that's an additional step people take. I don't think it's super necessary, which is why I kind of skipped it, but it's also perfectly fine to do it that way. Now what? So here's where so what we're doing is we're saying we're just going to let H of X equal f of X times g of X. So it'd be like saying H of X is equal to x squared times sine of X. And x squared is your f of X and sine of X is your g of X, for example. Then H of X plus H would be, well, I'm just subbing in an X plus H for each X. It'd be f of X plus H times g of X plus H. Or in the example I'm using over here, H of X plus H would be, instead of X squared, it'd be X plus H squared. Instead of sine of X, it'd be sine of X plus H. So what we're doing, we're using this renaming just to help us write the definition. So I'm saying, oh, the derivative of H is this limit. It's our usual limit definition. And then we're like, oh, but really capital H is little f times little g. And capital H is little f times little g. It's just that the inputs are different. And now it comes to the moment of somebody did this once and it worked. Like there was no way, maybe not no way, but unless you really knew what you were going for, you really wouldn't know where to go next. Here's where we go next. So I'm going to leave myself some space. I'm essentially going to write the exact same thing with some space in the middle. Give myself all the space. In the middle, I'm going to add and subtract the same exact thing. Specifically, I have to remember what it is. I'm looking for what. Okay, yeah. I'm going to subtract f of X times g of X plus H. I'm going to add the same thing. Why would I do that? Well, because it gets me what I want. Because somebody once one time showed me how to do it. I'm like, oh yeah, that totally works. So let's break this apart into two very convenient pieces. The first two pieces over H and the second two pieces over H. So the first two pieces, f of X plus H times g of X plus H minus f of X times g of X plus H all over H plus f of X times g of X plus H minus f of X times g of X all over H. And I'm going to ask you guys some questions. From this first piece here, from the numerator, what could I factor out? Right, the only thing that's the same in this part and this part is g of X plus H. So I'm going to rewrite this first part as f of X plus H minus f of X all over H times g of X plus H. And I factored it out from the numerator, but that's really a g of X plus H over 1. And from this second piece, what can I factor out from the numerator? F of X. And I'm left with a g of X plus H minus g of X all over H. And that was the part where we have to see the thing. What's the limit as H goes to 0? I should say, what's another name for the limit as H goes to 0 of f of X plus H minus f of X all over H? That's just the derivative of f as H goes to 0. And that's literally the limit definition of the derivative of f. And then this part here, this is just going to be g of x as h goes to 0, because the h is just going to become 0, and you're going to be left with g of x plus 0. F of x has no h's in it to worry about. And then this part here, now that we know what this is, I think you can all tell me what this is going to be. It's going to be what? It's going to be the derivative of g, because it's the same thing, right? We're taking the limit as h goes to 0 of g of x plus h minus g of x all over h. Oh, that's just the derivative of g. So look, we got what we wanted. This is exactly, it's like go fish, you got what you wanted. This is exactly f prime of x times g of x plus f of x times g prime of x. It's exactly the product rule. You should never actually need to reproduce this, but it's nice to see that the things we're saying are true are actually true, right? I mean, it's also good to believe things, but math is really true because it works. So we can use the product rule. We don't have a lot of things to take the products of so far, because we really only have powers of x we know how to differentiate and sine and cosine. So we could totally say, well, what's the derivative of x to the 7th power times cosine of x? And that would be, well, derivative of x to the 7th is 7x to the 6th times cosine of x plus, and then we flip it around. I would say vice versa, right? We kind of switch what we do with which. We get x to the 7th, and the derivative of cosine is negative sine of x. You don't need to write this, but you could certainly think of this being f, this being g, and then this being f prime times g plus f times g prime. I would slightly rewrite this as 7x to the 6th times cosine of x minus x to the 7th times sine of x. But that's the only real simplification that you would probably want to do here. Yeah, we're almost there. Yeah. Really wanted to show you the derivative of tangent. I'm not sure if we're going to get there. So there's also a quotient rule. And the thing I like to think about the quotient rule is it actually looks really, really similar in some ways to the product rule. So let's keep the product rule up here for just a second. The derivative of f times g is f prime g plus f g prime. Here's the quotient rule. Derivative of f divided by g is equal to, check out how the top of this is almost exactly the same as the product rule. It's f prime g minus f times g prime, which is almost the same as the product rule, just the sign is different. Divided by g squared. There's a couple ways of thinking about this. I usually remember it as the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. Those are literally the words I say in my head every time I do the quotient rule. But other people like to do this thing where they're like, it's the high and the low derivative, with the high over the low, and then they say it's low d high, meaning the low times the derivative of the high, minus high d low, all over low squared. Whatever way you want to remember it is perfectly fine, as long as you can remember it. It is definitely something, right? There's an expectation that you all learn and memorize the power rule, the product rule, the quotient rule, the chain rule when we get to it, and so on. Question? No. Trying to stay awake. I know it's not the most exciting material, but let's look at how much time. So let's do one example, and then I want to show you, we'll do more examples of this on Friday, but I want to show you one other thing. So let's say we want to take the derivative of something like x cubed plus 5 over x squared minus x. I'm really just going to throw the rule at it. right? There's nothing special here other than just you have to remember how it works. So that's going to be the bottom times the derivative of the top, which is 3x squared, minus the top times the derivative of the bottom, which is 2x minus 1, all divided by the bottom squared. And if there isn't a good reason to, you shouldn't simplify this. A good reason would be if you wanted to find where this thing was equal to 0, which we often do. So if you wanted to find where this derivative was equal to 0, then you would want to simplify it so that you could solve that equation. If we're not doing anything like that, you should just leave it alone. Another good reason to simplify is maybe that's going to make it easier to type into web work, right? Typing this into web work might be kind of terrible. It might be nice to simplify. One thing I want to mention is I did kind of do this first part in the opposite order, right? I didn't do f prime times g. I did g times f prime. That is totally fine. If I call this f and this g, this is g times f prime minus f times g prime all over g squared. That's just the way I usually think of it. It's the bottom times the, derivative of the top minus the top times the derivative of the bottom. As long as you can do it, doesn't matter how you say it in your head. All right, we've got less than 2 minutes, but I do want to show you the derivative of one more trig function. In fact, I will just let you know the other 4 trigonometric functions, tangent, cotangent, secant, and cosecant, all come from the quotient rule. I always say the chain rule when I mean the quotient rule. They all come from the quotient rule. So how am I going to find the derivative of tangent? Well, what's tangent as a quotient? Yeah, you know it. It's sine over cosine. So we're going to take the derivative of sine over cosine using the quotient rule. So it's the bottom times the derivative of the top. The derivative of sine is cosine minus the top times the derivative of the bottom, and the derivative of cosine is, yep, all divided by the denominator squared. But we're going to write it a little bit more nicely because this definitely simplifies. This ends up being cosine squared x minus sine times minus sine is plus sine squared x, all divided by, I'm going to write that as, instead of cosine x quantity squared, we're going to abbreviate it as cosine squared x. And who can tell me what the numerator is always equal to? Cosine squared x plus sine squared x is always equal to 1. And 1 over cosine of x is secant of x. So 1 over cosine squared x is secant squared of x. So the derivative of tangent is most commonly expressed as secant squared x. And next time we'll talk about the other ones. But you could find them all in the same sort of way.
Wait, so where did the cosine squared x plus sine x or sine squared x go?
So there's a trig identity that says, and so you're all welcome to go, but if you want to see the trig identity, bear with me for just 1 sec. Unit circle, angle, theta, the point on the unit circle that has a radius of 1 is the point cosine of theta comma sine of theta, but there's a triangle there. That part there is cosine theta, that part there is sine theta. This part here is 1, and the Pythagorean theorem tells us that this squared plus that squared equals that squared. So you get cosine squared theta plus sine squared theta equals 1. So this is known as one of the Pythagorean trigonometric identities, literally because it comes from the Pythagorean theorem. But it's always true that no matter what your angle is, if you have cosine squared of your angle plus sine squared of your angle, it's always, always, always equal to 1. So that's what happened there. That cosine squared x plus sine squared x got replaced with 1. All right, that's all I got.